Okay, we're going to start with exponential equations. I think they're actually the harder of the two because there's more options on what the equations can look like in the algebra that you have to do to solve them. We're going to be using the one-to-one property for exponential equations as our first choice. This is the easier option when solving. So our one-to-one property says if b to the x equals b to the y, then x is equal to y. So basically, if you can rewrite your exponential equation to be one exponential equal to one exponential, and the bases are the same, then you can just set the exponents equal to each other. So like I said, this is definitely the easier route. So for our general strategy, this is our first choice. We're going to try to see if this will work. So if both sides can be written as exponentials with the same base, do so and apply the one-to-one property. More than likely, it's not going to be ready to go. You're going to have to do some manipulation to get the bases the same. Well, if that doesn't work, our plan B is to rewrite our exponential equation in logarithmic form to get the variable out of the exponent and then solve the resulting equation. I think when we have to use this second technique, I'm going to show two different ways. There's one way that I usually only show. But because we're having to take MyMathLab exams, and the way that MyMathLab likes to do it is a little bit different. So I'm going to show you this other technique just because I don't want people having problems on the homework or having problems, more importantly, on the final exam. But I'm going to show you the way that I like you to do it as well. All right, so let's solve. We want to find the exact answer and the estimate answer to the nearest thousandth. So 2 to the x minus 1 equals 8. As I said, the one-to-one property, really, you want that to be your first choice. So you want to look at this and say, okay, well, I got one thing equal to one thing. Can I rewrite each of those things with the same exponential base? I have a base of 2 on the left side. Can 8 be rewritten as 2 raised to 1 some power?
Yes, that would be 2 to the third.
It'd be 2 to the third, so we want to do that. Now that we have written each side in terms of the same base, our one-to-one property says all you need to do is set these exponents equal to each other. And we get x minus 1 equals 3, making x equal to 4. Questions at all? All right, let's try another one. 4 to the x equals 32. So again, I have just one thing equal to one thing, so I'm going to sure try the one-to-one property. On the left, I have a base of 4. Can 32 be rewritten as 4 to some power? No, it doesn't work, right? 4 squared is 16 and 4 cubed is 34. I'm sorry, 64, and this is kind of in the middle. All right, well, before I give up on the ability to use the one-to-one property, I'm going to start with that first side, that 4, and say, well, can 4 be rewritten some other way? Because maybe it's the base inside of 4 that we can use for 32. So can 4 be rewritten as a number raised to a power?
2 squared.
Sure, it's 2 squared. So this becomes 2 squared to the x equal to 32. Remember, with our exponent rules, when you have a power raised up to a power, you multiply those exponents. This becomes 2 to the 2x equals 32. And now we start asking ourselves those same questions. Well, how about 2? Can 32 be rewritten as 2 raised to some power?
Huh?
2 to the 5th. We've now rewritten both sides with the same exponential base, so our one-to-one property allows us simply to set the exponents equal to each other and solve. 2x equals 5, making x equal to 5/2. Questions at all? Okay. Next, we want to solve 6 to the x equals 3 to the x plus 1. I have one thing equal to one thing, so I'm going to try to use my one-to-one property. I always start with the smaller base and see if I can rewrite the bigger number as the smaller base. So I have a base of 3 on the right. Can 6 be rewritten as 3 to some power?
No, it is 3 times 2.
Right, yeah, that doesn't work. And then I think, okay, well, let me try what I did in the other example. Can I rewrite the little number as a different base raised to a power? Can 3 be rewritten as some other number raised to a power? Nope, it doesn't work. So we're not going to be able to use the one-to-one property on this one. Instead, we're going to have to rewrite this in logarithmic form. So like I said, I'm going to do it two different ways. I'm going to show you the way I like you to do it first, and then I'm going to show you a different way, which I think is the way that MyMathLab likes your numbers to be accepted. The second way was actually the way that I was taught, but now that I'm a teacher, I realized I had no idea what I was doing with that second way. Like I could get the answer, but I didn't know why it worked, and I always like to try to present it in a way that you guys understand why we're doing what we're doing, not just do it because it works. All right, so we need to rewrite it in logarithmic form. We're going to use our conversion, y equals log base b of x is the same as b to the y equals x to convert. I recommend, because we can choose either of these bases to be our logarithmic base, 6 or 3, but I recommend that you choose the base with more terms in the exponent. So I would definitely use base 3 here. Rewriting this in logarithmic form using base 3, this is going to be log base 3 of 6 to the x is equal to x plus 1. Now, the reason we did this is because we're trying to get the variable out of the exponent so that we can solve for it, right? We never want it in the denominator. We don't want it inside parentheses. We want it free and clear so that we can get at the x so that we can solve it. In the first two examples, we were able to use the one-to-one property to get the variable out of the exponent. So here, we're using the logarithmic form to get it out of the exponent. So one of the x's here on the right has been successfully taken out of the exponent, but our second one is actually in worse shape than it was. It's in the exponent and inside the argument of a log. So we need to get this out of where it's at. All our log property number 7 says that if you have an exponent on the argument of your log, you can bring it out in front. This is going to be x times log base 3 of 6 equals x plus 1. And now both of the x's are accessible. They're not in exponents. They're not inside parentheses. They're where we can get at them and solve. Questions at all so far? All right, well, now we need to solve for x. You cannot just subtract 1 from both sides because x can't be equal to something with an x in it. But notice that x shows up more than once. both of the x's are linear, so typically we'd try to combine like terms, but the problem is that I can't combine it when it's attached to that log base 3 of 6. So we're going to have to go about it a slightly different way. We do want to get all the terms containing x on one side and all the other terms on the other side, just like we do when we're solving a linear x equation, right? All the x's together, all the constants on the other side. So we're going to put all the x terms on one side, everything else on the other side. Subtracting x over, it's just going to have to be tacked at the end because it doesn't combine. Once we do this, we now have a common factor of x on the left that can be factored out. And once we do that factoring, x only shows up one time, and we can solve for that one and only x. We'll divide both sides by this log base 3 of 6 minus 1. And we get the exact answer, x equals 1 over log base 3 of 6 minus 1. Questions?
So it would not have been correct to have divided the x out in front of the x in front of the log. It would not have been correct to divide that out.
No,
other
because if we did that, so if you divided everything by x,
Mhm.
now x is in the denominator over here.
Okay.
And chances are what people would do is just forget about the 1 and not divide it out there. And also, just in general, you never want to divide by the variable you're solving for because you're going to end up
Mhm.
losing answers.
Okay. Thank you.
Anybody else? Questions? The original directions asked for an exact and an approximate to the nearest thousandth. So we need to get a decimal approximation here. It's log base 3, so our calculator is not going to be able to do that. We're going to have to use change of base formula to get the approximate answer. And you definitely want to get your calculator out for this so that you have the opportunity to practice typing this in.
So approximately 1.585.
Well, hold on. You're way ahead of me, Anthony. Hold on. All right. So this 1 over log base 3 is 6 minus 1. The change of base formula has to happen in the denominator. And I'm going to use natural log. Log base 3 of 6 turns into natural log of 6 divided by natural log of 3. And then this minus 1 is off to the side, but still in the denominator. When you plug this in your calculator, be sure to have this denominator in parentheses. And now I'm ready, Anthony. What did you get?
Approximately 1.585.
1.585. So please make sure that you can plug that in. I'm going to give everybody a minute to plug that in. If anybody's having any issues with their calculator, it's important that you let me know.
I can't get it on my calculator.
All right, I'm going to share my screen and then try to look at your video. You have to turn your video on though.
Oh, okay.
And then shove your calculator in the, in the camera. All right, hold on. I gotta pin this so I can see it. Okay.
Like which am I supposed to be putting the?
All right. So put 1 and then divided by,
Yeah.
and then open up a parenthesis,
Mm-hmm.
and then natural log of 6 divided by natural log of 3, and then minus 1, and then close your parenthesis.
Okay.
Good?
Yep.
Great. Anybody else? All right. So now I just want to do the same problem another way, which again, I'm like 99% sure that this is how my math lab likes it. And some of the other instructors even teach it this way, but like I said, I feel like I like this technique that I showed you because we're already using all the things that we've already learned. We're not learning something new. We're just reinforcing what we've already done. And I always like to remember less stuff. What we're going to be doing here is kind of using what's called the one-to-one property for logs. Almost in reverse here. I'm going to jump forward to where the logs are. So the log one-to-one property says that if log base b of x is equal to log base b of y, then x equals y. So if you can rewrite it, 1 log equal to 1 log, and the bases are the same, the arguments have to be the same as well. Well, this technique is kind of taking this one-to-one property and going this way, and basically saying if you have two things that are equal to each other, you can just slap a log of the same base on the outside of each of them and make whatever your original equation was the arguments. See, like that's weird to me, even to say it right there. It was weird. So in this technique, like I said, we're going to use the one-to-one property for logs. In reverse, well, in one of the directions. So if I have 6 to the x equal to 3 to the x plus 1, if I'm using this property kind of in reverse, instead of taking the logs away, I'm going to add the logs. And you can use log of any base you feel like it, but why wouldn't we want to use a log base that is compatible with our calculator? And typically they use natural log and not common log. So basically what happens is you take the ln of each side. We're still trying to solve for x, and we notice that x is in the exponent on both sides. So we're going to use our log property number 7 and take each of these exponents and put them out in front of our natural log. This is going to give us x times the natural log of 6 equals, now careful, this second exponent is a binomial, so you need to be sure to put it in parentheses when you put it out in front. We'll distribute on the right because I have to get to both of these x's, so I need to get it out of the parentheses so I can get to it and solve. Any questions so far? Well, now we're to the same place we were when we use the other technique. I'm trying to solve for x. It shows up more than once, both linear. So we're going to get all the terms containing x on one side, all the terms that don't have an x on the other side, and then we're going to factor the x out and divide. We get x times the natural log of 6 minus x times the natural log of 3 equal to the natural log of 3. We factor that x out. And then we divide by what we have in our parentheses. We get x to be equal to the natural log of 3 divided by the natural log of 6 minus the natural log of 3. And that is our exact answer. Questions?
Wouldn't we cancel out the natural log of 3?
Definitely not. You only can cancel if it's a common factor, and that natural log of 3 and the denominator is not a factor, it's a term. So you see that our two exact answers look really different, but let's get the approximate answer and we'll see that we get the same. Now, the one advantage to this technique is you don't have to do change of base formula to get the approximate. It's already ready to go because it's a natural log form. So let's put this in our calculator. Be sure to put the logs in the denominator in parentheses. And what do we get for x?
1.585.
So we do get the exact same answer. It's just our exact answers can look the same. And I feel like my math lab always says, write your answer in terms of the natural log. So they're looking for this second technique. I just don't think it makes as much sense as the first technique. Questions, anybody?
Couldn't you divide out the ln3?
No, so that's what Anthony had asked. We can't do that because it's not a factor. That'd be like having, I don't know,
Oh, because they're together in the bottom. Okay. Nice.
like 15 over x minus 5 and then simplifying the 15 and the x. We can't do that. Or even if, I guess, more parallel would be the 5. We can't simplify that.
The linear 1 there blocking you from doing that, basically, or whatever.
What do you mean?
Like, since it's like ln minus 1 ln3, you can't do that.
Right.
Gotcha.
Anybody else? I know it's sometimes can be hard for us to see algebra rules that we know when the fraction looks so different now.
Yeah.
So remember that you can always just strip it down then to something that you are comfortable with. You know, would I cancel those 3s? Although that was a horrible example because I could factor 3 out of the denominator. All right, let's try another one. One thing equal to one thing. I'm always going for that one-to-one property first. I can't rewrite 8 as 9 to some power or 9 as 8 to some power. I can rewrite 9 as base 3 and rewrite 8 as base 2, but none of those match up. So again, we're going to have to rewrite it in the logarithmic form. And again, I'm going to show you both ways. Rewriting it in terms of one of these bases, I would definitely pick log base 9 since 9 has more terms in the exponent. So this becomes log base 9 of 8 to the 3x equals 2x minus 4. And then it really is, I mean, you're just doing the same thing over and over and over again with each of these problems. We start by putting our exponent as a coefficient, and we know we want to do this because we're trying to gain access to this x, so I need to get it out of the log and out of the exponent. Next, we want to get all the terms that contain an x on one side and all the terms that don't contain an x on the opposite side. We're not going to be able to combine this when we move it over, so we just tack it on the end. Now that we have a common factor of x on the left, we can factor that out. We're left with 3 log base 9 of 8 minus 2. And then last but not least, we will divide by that stuff in the brackets. And there's our exact answer. Questions, anybody? To get the approximate, we'll have to use change of base formula again. So we have this 3 out in front because we know that, we're going to turn that log base 9 of 8 into natural log of 8 over natural log of 9. You could put that 3 just kind of floating out in front, but I don't know. I'd rather put it somewhere. Remember that that's 3 over 1. So if I multiply these two together, that 3 is going to go in the numerator. And then minus 2. Be sure to put this denominator in parentheses when you put it in your calculator. And I also recommend that everybody's trying every time so that we don't have any calculator issues come test time.
Negative 3.347.
Anybody else get that?
I got negative 4.767. So I might have put
That's what
something
I
else.
have in my notes.
That's what I got too.
Yeah.
All right, Anthony, give it a try again.
Oh yeah, negative 4.767.
There we go. All right, I'm going to do this problem a second time, again, using just the natural log. We are starting with 9 to the 2x minus 4 equals 8 to the 3x, and using the 1-to-1 property for logs, I'm going to make each side the argument of a natural log. Our variables are still in the exponent, so we're going to get them out of the exponents by using log property number 7 and bringing them out in front as coefficients. Be sure any of them that are binomials or anything other than a monomial, be sure to put it in parentheses. So 2x minus 4 times the natural log of 9 equals 3x times the natural log of 8. We'll distribute on the left, so that second x is not in the parentheses. We have 2 linear x's showing up, so we need to get all of those x's on one side and all the terms that don't have an x on the other side. So I guess I'm taking this first one and moving it over to the right. Or you could do a double switch if you didn't have the negatives. If you did not want to have all the negatives. Now we have a common factor of x on the right that we can factor out. Even if you have more than, like your GCF is more than x, don't ever factor anything more than the x out, because that's what we're trying to solve for. So if there was a GCF of 3x or something like that, leave the 3. And then we'll divide both sides by what we have in the bracket. We'll get x to be equal to -4 times the natural log of 9 over 3 natural log of 8 minus 2 natural log of 9. This is ready to go to plug into our calculator for an approximate answer. Just be sure that you're putting this denominator in parentheses. We should get that negative 4.767 again. Questions, anybody? All right, so this next one, I would not put this on a test. I would put this on a test in pre-calc when we review this, but I would not put that on the test here. You might see it, it could be on the take-home quiz. You might see it on the homework, but there will not be one where there's multiple terms in both exponents on the exam unless you can use the one-to-one property to solve. All right, so there's only one slight difference here, and I think I'm gonna put you guys in rooms and let you work on this one. So there's only one difference. Everything is exactly the same. The only difference is when you bring the exponents out in front, because they're both binomials, they both need parentheses, and you're going to have to distribute on both sides of the equation. Like you won't, oh no, I guess you won't have to on both. No, it'll just end up being like this side. With the technique I showed you there, if you chose the exponent with more, if you chose the base that had more terms than the exponent, we didn't have to remember to put parentheses around the exponent and then distribute. With that natural log technique, we had to do that every time. With this one, because both exponents are binomials, you're just going to have to either do that once if you use the technique that I demonstrated on the left, or you're going to have to distribute right twice on both sides of the equation if you use the technique that I demonstrated on the right. So, all right, I'm going to break you guys up into rooms and let you work on this.
So we're using both techniques.
You can use either technique. I don't care. You know, of course, I need you guys to practice the technique on the right. That isn't my preference because I want you to be successful on the exams. But I like the technique on the left because I think it reinforces what we're doing. And it makes more sense with what we've already learned, not just, oh, slap a log on both sides and now you can do this. But I don't care which technique you use right now. All right, I think I'm going to make big groups because this isn't a, you know, it's kind of a tough problem. So I think I'm going to put 5 of you together. Be sure to talk to each other. But thank you. That's why your recording is always recorded, and I forget half the time with my Tuesday, Thursday. So half the time they get this recording. So I do appreciate the reminder. I did this problem 3 different ways. I did it my preferred technique the first 2 ways, but I did it twice because you could have used log base 2 and you could have used log base 5. So I wanted to do them both so that you guys could see that. And then I did it, the third technique, the way I did it was using the preferred Pearson technique here. So I'll give you a second to compare the answers. I don't have this one in my notes, so I do not have a decimal approximation for it. I'm sorry, Madison, were you giving me a decimal approximation?
Oh, sorry. No, but I did. Okay, I can.
Would you? That'd be great. I didn't mean to call you out. I just thought I heard you talking.
What I got was negative 1.0294.
0294, but we're going to go to the nearest, what are we going to, thousandths? So that's just going to be 9. Anybody else get that?
Yeah, I got that.
Okay,
After the 7 attempts, I got that.
great. Just attempts of getting it in the calculator. Yeah, it's really important. We got to get the numerator and denominator in.
Yeah, I ended up having to like break it apart in my calculator to get the right answer.
Okay, that's why we practice on our calculator, so we get comfortable with this.
The break apart, you mean by using the built-in parentheses or having to write down two separate answers?
Yeah, like I did it, like I calculated what the numerator was, and then calculated what the denominator was, and then divided it out.
We're using this kind of calculator.
Oh, she can't see you. All she can see is my screen. That's
I
fine.
have
As long as
a-
she's comfortable with it. If she wants to ask me questions about her calculator, we can do that after class.
Because I found, I used to think you couldn't do parentheses within other parentheses, but you just have to write it, to enter it carefully, and then you can do embedded parentheses.
Yeah, because the only thing, Elena, you gotta be careful about doing the numerator, unless you're like saving the answer in the memory of your calculator, that, you know, if we round too early, our answer can get a little bit off. So if you are gonna do that, make sure you're taking every single decimal place that they give you.
Yeah, definitely.
Okay. So everybody got one of those exact answers though, and then they all should give us the same approximate. Again, that one's tough. I usually don't put that on the test. Okay. Oh, geez. Our next example looks a little bit different. E to the 2x minus 4 e to the x minus 5 equals 0. Notice for the first time, we have more than just one thing equal to one thing. We have 3 things equal to 0. And even if I rearranged it and moved the 5 over, I would still have 2 things equal to one thing. Oh, because of that, that rules out one-to-one property immediately, because that has to be one thing equal to one thing. Sorry, thing's the most technical word I can come up with. Then our second technique, like our plan B, was, well, rewrite it in logarithmic form. But that logarithmic form only works when we have an exponential equal to one thing. So neither of the two techniques that we've done so far are going to work here. We're going to need to do some algebraic manipulation before we try to get the variable out of the exponent. You've actually practiced working on this before in preparation for this. This is one that we are going to factor by substitution. We know that this is quadratic in form because once we have written our terms in descending order, we notice that the second exponent is half of the first and the third term is a constant. So we want to factor this. If you're comfortable factoring this without the substitution, you're more than welcome to do that. I'm going to write out the substitution. We're going to let y equal, what should we let y be?
E to the x.
E to the x. It's always, when you have it in descending order, it's always the variable portion of the second term. We're going to have y equals e to the x. That transforms our equation to y squared minus 4y minus 5 equals 0, which will factor nicely into y minus 5 times y plus 1 equals 0. Once we get it into the factored form, we're going to plug e to the x back in for y. And that's going to give us e to the x minus 5 times e to the x plus 1 equals 0. Applying zero product property, we're now going to set each one of these factors equal to 0 and solve. Anytime you're dealing with e to the x, one-to-one property is not going to work because e is an irrational number. We're never going to be able to rewrite another number in terms of e. So we're going to have to use the technique about rewriting in terms of a log. And because our base is e here, whether you use my preferred technique or that ln technique, we're actually going to get the same thing. For either of those techniques, though, you need the exponential isolated. So we'll take e to the x is equal to 5. And then I feel like most of the people are doing the ln because of the MyMathLab, so I'm going to do it this way. Now, this is where one of our properties, one of our inverse properties, I think it was property number 3 for logarithms, we talked about how if the exponential base and the logarithmic base were the same, they canceled each other out. Well, natural log and base e cancel each other out. This leaves us with just x equals the natural log of 5. Which is the exact same thing if you would have just rewrote it the way that we've been practicing. For the next one, we're going to do the same thing. We'll isolate our exponential. And then we can either natural log both sides or rewrite it the other way. Either way, we're going to get x is equal to the natural log of -1. What do we know about the number inside of a log?
It can't be negative.
Yeah, it can't be 0 either. So this must be positive, the argument. And since it's not, we got to throw this answer out. So only one answer. And let's get the decimal approximation for this as well. Just goes right in our calculator since it's natural log. 1.609. Questions, anybody? All right, let's do an application then. We want to find the population of the population of a city is P equals 250,342 times e to the 0.012 t power, where t represents the population in the year 2000. We want to find when, like what year, the population will be 320,000. What do we need to do to set this up?
Plug in 320,000 for P.
You got it. Oh, since we only have one term on each side, we shouldn't have to factor. We should either be able to use the one-to-one property or rewrite it as a log. Since our base is E, we know it's not going to be one-to-one property. So this is one where we're going to rewrite it as a log. You want to isolate the exponential portion first. So let's divide. This is not going to be a nice number when you divide. And we don't want to start with a decimal on our first move. So we're actually going to keep this gross fraction. Maybe it simplifies some, but I feel like I don't want to waste my time doing that because I'm going to have to plug this in my calculator anyways. And I might make a mistake when I'm simplifying. So I'm just going to leave it. Now that we have the exponential isolated, we're ready to rewrite it in logarithmic form. So we can make this the argument of a natural log. Or again, if you rewrite it using my technique, this is exponential base e, so we're going to rewrite it as logarithmic base e. We're going to get the exact same thing. We have the natural log of 320,000 over 250,000, 342. And then we got to remember that our logarithmic base e and our exponential base e cancel out, leaving us with just the exponent. The last thing we need to do to solve for t is divide. And we just pop this in our calculator, solve for t. Anybody get an answer for t?
I got 20.458.
Anybody else get that?
That's what I got.
Yes, 20.45.
Great. So now let's make sure we've answered the question. It said, when is the population going to be 320,000? But t represents the, okay, so it says t equals 0 represents the population in the year 20. So t is in the year 2000. So t represents the number of years after 2000. So if we're going to go 20.458 years after the year 2000, what year does that bring us to?
The year
2021.
2021. I know when you add these together, you get 2020.458. And even if you were just rounding, you'd probably think round down, but that's not how our calendar works. You know, as soon as we hit that new year, we don't have to be through the whole thing. So we're going 20 years after 2020. So we've completed 20 whole years. And now we're going half a year into the following year. So this is like May 2021. So always round up no matter what when you're doing years like this. Unless the question is how many years, but if it's asking like what calendar year we're talking about, always round up. Questions at all? All right, I think I want to jump to some of the application problems rather than starting logs. Let's get an application problem in. Page 225, exponential growth and decay. So I said that there'd be more challenging application problems later on in chapter 4, and so here they are. The mathematical model for exponential growth or decay is given by a equals a sub 0 times e to the kt power, where a sub 0 is the original amount or size when our time t equals 0, a is the amount at time t, and k is a constant representing the growth or decay. If your k value is a positive number, your amount is growing. If your k value is a negative, then your amount is decreasing or decaying. In 1990, the population of Africa was 643 million, and by 2000 it had grown to 813 million. We want to find the exponential growth function that models the data in which t is the number of years after 1990. We want to round our k value to 5 decimal places. And then once we get that model, we're going to use it to solve part B and answer the question, by which year will Africa's population reach 2 billion? These problems to me are super similar to the variation problems that we did, where you'd start by writing a generic equation, you'd plug in things that you knew and solve for your k value, then you rewrote your equation with the k value in it, and then didn't use that new equation to answer a question. That's really the procedure that we're going to be doing here. It's just the way that we solve for k is a different technique because we're going to have an exponential. And you don't have to come up with the original generic formula because it's always a equals a sub 0 times e to the kt power. We want to plug in for all variables except k. So we need an a sub 0, and a t. An amount after a certain amount of time, the original amount, and what that amount of time was. So what do we know?
Oh,
Well, what was our original amount? And we're talking about the population, so we're looking for the original population in the discussion.
643 million?
So that's going to be our a sub 0. Then we need an amount after a certain amount of time. So what's our second amount after time has gone by?
813.
So that's our a. And then we need to figure out, well, how much time? We went from 1990 to 2000.
10 years.
So that tells us our t is equal to 10. So we're just going to plug those 3 numbers in and solve for k. $813 equals 643 times e to the k times 10 power. I'm going to rewrite my exponent there. And we want to solve for k, which is a variable located in the exponent. So we're solving an exponential equation. We always want to isolate the exponential first. So we'll divide by 643. Again, I would not waste any time trying to simplify this fraction over here. Just going to leave it and plug it in my calculator. We're ready to rewrite it in logarithmic form. We'll get the natural log of 813 over 643 equals 10 to the x. And again, either technique, either putting the natural log on either side and then canceling your natural log with your exponential base e, or just rewriting it using our circle technique for logs and exponentials. We get this. And then to solve for k, we'll have to divide by 10. It told us we want to go 5 decimal places on that k. Since the population is growing, I'm anticipating a positive k value. But our k values are usually very small numbers. I'm getting 0.02346. But we're not quite done. Now we actually have to write the function. And the directions say find the exponential growth function that models the data in which t is the number of years after 1990. Well, since they're giving us an initial year, we're going to substitute in not only our k value, but our initial amount a sub 0, and we're going to get a equals 643 times e to the 0.02346 t power.
So what are we looking for in the first place?
Well, we're writing a growth function that models the data. That's what we're doing in this first part. Now we'll use this function to help us answer questions that's asked in part B. Anybody else before we do part B? All right, I'm going to rewrite my function just so I can see it. Oh, part B says, by which year will Africa's population reach 2 billion? So that 2 billion represents which of my variables?
A.
That represents our A. So that's our new A. But you'll notice all the other amounts were not in terms of billions. They were in terms of millions. So I can't plug billions into an equation that was designed for millions. So we need to rewrite 2 billion in terms of millions. How many millions is 2 billion?
2000.
1,000.
2,000. So we're plugging that in for A. Got to be in the same kind of unit. And although we're solving for a different variable in the exponent, our procedure here is exactly the same as part A. We're going to isolate the exponential portion. We're going to rewrite it in log form and finish solving for the variable. Our logarithmic rewrite becomes the natural log of 2,000 over 643 equals 0.02346 t. And then we'll divide to finish solving for t. T equals the natural log of 2,000 over 643, all that divided by 0.02346. So what do we get for T?
48.164.
48.164?
Yeah, 164.
I got 48.3698 and so on.
Same, 48.3698.
All right.
All
All right, so just try that again, Layla. You just must have typed in the wrong number. But what was the question? By which year? So the year is not 48, right? Remember that T represents the number of years after 1990. So to actually answer the question here, we're going to have to do 1990 plus this 48.3698. And we always remember, Joel, can you mute your mic?
Oh, sorry.
Thanks. And remember that we always round up because we're pushing into the next year. Wow, I wrote 1900 instead of 1990 there. So if we do that and we round up, it ends up being the year 2039. This is a super typical problem. You are going to see one very similar to this on the final exam. So the rest of this week, so the rest of the week, you guys have your exam. We're not going to have class on Wednesday because the exam is going to start Wednesday morning and I'll run it through Friday at midnight. Then next week, oh my gosh, next week is our last week. I feel like it's crazy that this is flying by here all of a sudden. So next week is our last week. On Monday, I'm going to finish the material. We're going to do a couple more examples of this exponential growth and decay applications. And then we're going to do a handful of solving logarithmic equations. I'm definitely going to get it all done on Monday. And then Wednesday is going to be a review day where basically I'm just going to be here and you guys are going to ask me questions and I'm going to start working out the questions for you. And then the following week is the final exam. They did send a final exam schedule, but I didn't look at it yet. I'm going to probably, I don't know what I'm going to do for the final yet. I gotta get through writing the test that I need done for this week, and then I'm gonna think about the final exam, whether I'm gonna do multiple attempts, whether I'm gonna do a single attempt, and you have to like log in a specific time, and I watch you guys take it over Zoom so that I know that you're the one taking your final. I haven't quite decided what I'm gonna do, so I gotta figure all that out in the next couple days, and I will definitely let you know. But yeah, that's the plan for the course. There is a final exam review packet with a fully worked out answer key posted in D2L. So as soon as you finish your exam this week, I would start working on that final exam review packet. Now there's going to be a little bit of stuff, anything that has to do with matrices, like rectangles with a bunch of numbers in it, you can just skip all those because that's the Unit 5 material that we are skipping. So. Anybody, questions for me?
We don't have class Wednesday, you said?
Correct. No class on Wednesday because you guys have your exam to take.
Okay.
Anybody else? Any questions? All right. Well, I'll be on for a half an hour for office hours, and then I also have office hours this evening at 6:30, and then I can also do by appointment if none of that works for you guys. Otherwise, have a wonderful day. Good luck on your tests, and I will see you on Monday.
Thank you.
Good day.